all the reactions here involved alkenes, alkanes in terms of radical substitution, alcohols, elimination, and substitution reactions. So with question A, we're given this bicyclic compound which has an alkene, and the reagent that's used is phosphorus oxychloride in pyridine. We know that POCl3 is a dehydrating agent, which means it takes our substrate and dehydrates it into an alkene. In order for this reagent to function as intended, we need to have an OH in our reactant, which then reacts with phosphorus oxychloride to yield the dehydrated product. So let's start out by drawing the carbon backbone. The presence of the OH group is critical for dehydration by POCl3. What happens is that the OH group nucleophilically attacks the phosphorus in phosphorus oxychloride, and one of these chlorines is kicked out to form the first intermediate right here. In the second step, pyridine comes in as a base and deprotonates this compound. Because we don't have a hydrogen here, and the alkene forms directly adjacent to the bridgehead carbon, these hydrogens here are the only possible targets for pyridine. So pyridine is able to pluck off this proton and send the electrons back into the compound. This causes this substituent to leave, and it turns out POCl2OH is a very good leaving group. Therefore, the net result is the compound is dehydrated. In B, we have this phenyl substituent and the bromine on a wedge, which undergoes some reaction with some unknown reagent forming product X. X then undergoes another reaction to form a cis diol. So far, the only way we can form a cis diol is by introducing osmium tetroxide in the first step and sodium hydrogen sulfide in the second step. But the substrate for dihydroxylation is an alkene, so I assume that compound X is an alkene. But the compound we begin with has no double bonds, but I do notice the leaving group. So essentially, we have a secondary bromide, and we must eliminate the compound to form the alkene between these two carbons. And because we're assuming it's a one-step reaction, it must be an E2 reaction. Now, characteristically, E2 reactions must involve a strong base that is generally non-nucleophilic. One such base is sodium ethoxide, which can be abbreviated like this. And by convention, the reaction occurs in the conjugate acid, ethanol, the polar protic solvent, and just to ensure that elimination occurs, we can apply heat as well. Now we need to be really careful with this because this is an E2 reaction, and we know the leaving group leaves, and we know the base can come in and pluck off adjacent hydrogens. We know it's generally not a very bulky base, but the question is, do we form the Zaitsev product, which is the alkene right here, or the alkene right here? Because if we form the alkene right here, we wouldn't form this dihydroxylation product. Another clue is that if we form the double bond right here, it can conjugate with the phenyl group. So this brings up a very important exception to the Zaitsev rule. If we're doing an elimination reaction and we have a benzene substituent, the conjugated product is always favored. Resonance energy will drive the reaction such that the anti-Zaitsev product will form. So the result of this reaction is the bromine leaves and the ethoxide anion can pluck off this hydrogen right here, which then allows the electrons to flow back into the compound to form the conjugated product. Now with this example, we're given methyl cyclopentene, which reacts with thionyl chloride in pyridine. The way thionyl chloride functions is that it needs an OH group in the substrate, which can nucleophilically attack the sulfur and kick out one of these chlorines. So here's sort of a summarized mechanism. Oxygen can nucleophilically attack the sulfur, kicking out a leaving group, which results in this group remaining on a wedge. In the second step in the mechanism, pyridine can deprotonate the compound, which then yields a neutral charge. What then happens is that the compound spontaneously decomposes, which causes the formation of SO2, and a floating chloride can nucleophilically attack this carbon right here from the back in this case, to form the inverted product. The net result is that the reaction can substitute an OH for a chlorine in the process, inverting the chiral center. In this case, methylcyclopentene can't react in the way that's described here because we don't have the OH group, so this reaction does not occur. Question D involves alcohol and radical reactions together in a mini-synthesis. In the first step, sulfuric acid and heat will cause the formation of X, which then undergoes allylic bromination with NBS to form the product. What I found most useful in solving these problems is just to write a mini mechanism towards the side. So H2SO4 in high heat, vigorous conditions, causes the dehydration of the compound, just like phosphorus oxychloride. But in this case, it's acid catalyzed and rearrangements can occur. So to start, H2SO4 can protonate the OH group, which acts as a very mild base. The generation of this positive charge in H2O means we formed a good leaving group. Now, just like we saw with exam 2 material, a secondary carbocation has formed directly adjacent to a quaternary site, a quaternary carbon. So this means a 1,2 methyl shift will occur. And in the final step, the leaving group water can come in and deprotonate an adjacent hydrogen. The electrons travel back into the compound, and the net result is the dehydrated compound, the Zaitsev alkene. Now we know that allylic bromination does not disturb the pi bond, and instead adds a bromine directly adjacent to the sp2 carbon. So if we use this alkene here and place it with NBS in dichloromethane and light irradiation, what will happen is that the pi bond is not disturbed and we form bromine directly adjacent to the pi system. Now, question E has many unknowns. We're given a primary alcohol which reacts with some reagent to form compound X. Compound X can then react with what seems to be a strong base, sodium methoxide, in a polar aprotic solvent to form the product. Now, because we have a lot of unknowns here, let's try to figure out what this mini synthesis is like using all of our skills. To start, polar aprotic solvents were used and will continue to be used with SN2 reactions only. DMF is a polar aprotic solvent. Like DMSO, it does not interfere with the negatively charged nucleophile, which allows for the promotion of SN2 reactions. In this case, sodium methoxide is our nucleophile. The question is, what is compound X, and what are the characteristics of compound X that allow it to be susceptible for an SN2 reaction? We know that primary alkyl halides are good contenders for SN2 reactions, but what's implied here is that you can synthesize a particular compound X that contains a great leaving group, which can jump off the compound and allow for the formation of the ether. One way to do that is with tosylate ester synthesis. To this alcohol, we can add tosyl chloride in pyridine, which when gone to completion gives us our tosylate ester, and we can abbreviate that with OTS. The tosylate ester presents one of the best leaving groups, which allows for simple SN2 reactions with a strong enough nucleophile in an aprotic solvent. If we expanded this structure here, we would see why the tosylate ester is perfect for SN2 reactions, and why the tosylate is a very good leaving group. If any particular nucleophile can attack the ester, the result is a negative charge will accumulate on this oxygen, forming the tosylate ion. And you can tell that this negative charge can be extensively delocalized across this entire structure, which means this is a very good leaving group in general, as long as we have a strong nucleophile in an aprotic solvent. The net result is that the tosylate ester is attacked by the methoxide to form methyl propyl ether. Now in question F, we're given an alkane here, isopentane, and through some reagent and solvent or conditions, we can form the bromine on the tertiary position. One clue here is that we have no alkene, so we can rule out any electrophilic addition. The only way to substitute A bromine on an alkane is through free radical substitution. In this case, the tertiary position is very highly favored, with a relative rate close to 1600. So the reagents that are used is Br2 diatomic, dichloromethane as the reaction solvent, and H-mu.